All right, stats. So we're in a little bit of uncharted territory for us. We're going to do our first chapter where I have had absolutely no contact with you about this chapter before we started. So don't be surprised if we don't go into as much detail, if we go a little bit slower, mainly because this is all going to be brand new. Now, this is called a chi-square goodness of fit test. I know it's CHI, which some of you might want to say chi or chai, but it is pronounced chi. Now, this test, the goodness of fit test, is not on every version of a graphing calculator. So the first thing I need you to do is make sure you have this before you can proceed. So on your calculator, you're going to press Stat. You're going to go over to the Test menu. You're going to go way down to the bottom of the list. So I'm just going to press Up, which will take me to the bottom. You'll see that option D in my list says, it looks like an X, but that is the symbol for chi, square, GOF, which stands for goodness of fit. If you do not have that on your graphing calculator, you're probably going to want to use the website I'm showing you right here. Remember that email that I sent you? Hopefully you saved it, and then you can pull it up on your phone or any tablet device. Okay, so we will need that when we get to it. Now, what exactly is a chi-square goodness of fit test used for? Mainly, you want to think of it this way. All of our tests have either been comparing a value to what we think it should be or comparing two values against each other. In a chi-square test, you will be actually checking that multiple values all fit some sort of what you believe to be known distribution. So this allows us to compare more than two things. And that's where the chi-squared test is actually very, very useful. Now, the truth is, the chi-squared testing that we do is very, very basic. And in a real-world scenario, it would probably represent step one of a huge process in testing. But nonetheless, it still has its importance, and we're going to look at it. So the test statistic for a chi-squared test is the chi-squared. You won't see a Z, you won't see a T, you'll see that italicized looking X with a square on it, and that's known as chi-squared. When we are running these tests, we need to look for observed values, which is what actually happens, and compare them to expected values. Now, when we started off testing, one of our big examples was a coin. It was real easy to say, what do you expect to happen on a coin? And just about everybody will say, well, half the time it lands heads, half the time it lands tails. Well, a coin has only two outcomes, which is why it's great when you talk about Z tests. But for chi-squared tests, we're going to need something with more than two outcomes. And needless to say, when it comes to statistics and probability, one of the favorite things for people to use is a die. So we're going to look at a standard six-sided die. Look at the chart. You can see that there are 6 outcomes, and they have rolled this die 60 times. 60, of course, was chosen because if this is a perfectly even die, 60 is nicely divisible by 6, and that means you would expect all 6 of the sides to occur about 10 times each. What you observe doesn't necessarily have to be exactly 10 each, but the results should be close to that. What we can do is we can take the data that was actually provided and see if the results are consistent with what you expect. And that is what a goodness of fit test does. It compares actual results to expected results to see if you get what you think you should get. So this data will be entered in on the calculator through lists, and we will be putting our observed values, so what actually happens in list 1, and we'll be putting our expected values, what we believe should happen, in list 2. So notice that the outcome values of 1 through 6 They put those in their chart. We would not be entering those, though, into the calculator. So I don't necessarily want to do this first example right off the bat, because honestly, the rest of the stuff they show us is doing a lot of it by hand, which you know we don't really do. So you can see in this example here that they're running all the information and they're getting the values that are necessary to eventually get the test statistic. We won't worry about that because, of course, the calculator will spit all that out for us. What we want to do is we want to look at some of the different things about a chi-squared that we wouldn't have known. So going into this, you need to realize that chi-squared distributions very rarely will ever be normal. Z distributions are normal. T distributions become more and more normal. Chi-squared distributions will almost always be skewed. So, if you look at the first two, you can tell that they're skewed right. If we look down here at the next few, we can see that they're also mostly skewed right. Look what caused the distributions to become more normal. Instead of them rolling the dice more, they have actually compared different types of dice. We have a 4-sided die, a 6-sided die, an 8, a 12, and a 20. Every time the die has more sides, you get a more normal distribution, mainly because there's more outcomes that can occur. But here's the thing. You don't have control over that. If my goal is to test and see that a 6-sided die is fair, I can't make it a 12 or a 20-sided die just to make sure that the result is more normal. But the good news is we don't really care about the distribution being normal because the calculator has the ability to take into account what the distribution looks like based on the number of outcomes. But it is important for you to know that you can't force this distribution to be normal by performing the task more times. If I roll a 6-sided die 60 times, and if I roll a 6-sided die 6,000 times, the distribution will still be skewed right. I have no control. I can't stop it. So that means that these distributions don't ever really end up being all that similar to our other testing that we've done. We have to rely on the calculator to just kind of tell us the result. That means that for you guys, your test statistic isn't going to have as much meaning as it did in the other ones. You're not going to be able to look at your test statistic and be like, oh yeah, I know that's an extreme value. It fluctuates depending on how many outcomes there are. So really, we're going to be focusing on the p-value because the good news is that interpretation still doesn't change. Any p-value that's less than 10% is statistically significant, at least at some of our values. And if it's under 1%, that p-value is statistically significant at all of our major levels. So that kind of interpretation will not change. Now, let us go ahead and rather than look at them doing stuff by hand, let's scroll all the way down to the important box that tells us how we're going to do these tests. And yes, we're jumping straight into the tests. There is no confidence interval that we will conduct on chi-squared. So this is called a chi-square goodness of fit test. That's it. Checking the conditions. I have no idea why they're in the order they're in, but I'm going to look at bullet point 3 first. We still want a random sample. So obviously a random sample. Now I'm going to go back up to the top. Each outcome can fall into only one category. So for a die, that's pretty easy. Yes, every outcome can only occur at, once. But if I were to take, let's say, groups of students and break them up by the clubs they are involved in, and I wanted to see if the distribution of participation was the same across all the different clubs, I wouldn't be able to use a goodness of fit test because there would be a lot of people who are involved in multiple clubs. So that just doesn't work. So you have to make sure that the outcomes are all completely and totally non-overlapping. That second bullet point says you have to have a model. Now for something like a die, we expect them all to occur equally likely. But for other information, they either have to tell you that all the results should be equally likely, or they have to tell you about what the results should be. So you need to know that if there's, let's say, 4 outcomes, that 20% of them are in outcome 1, 30% are in outcome 2, 25% are in outcome 3, and 25% are in outcome 4. If they don't give you that model, you're not going to be able to get the expected values. And then finally, all the expected values need to be at least 5. If they're not, then they say that that is not enough information in order to properly do the analysis. Now, getting at least 5 in each expected value really should, for the most part, not be all that difficult. You're going to state your hypotheses. The null hypothesis should be that the distribution of outcomes is equal to whatever their model is. So basically, if I was rolling a die, I could say something along the lines of the distribution of outcomes for each side of the die should be 1/6. Done. And then I can go on. For the alternative hypothesis, and this is key here, read those first 3 words. At least one. So at least one of your outcomes is not equal to what you expected. That doesn't mean that they're all different. It just means that at least one of them didn't fit the trend. So this is why this test is not super duper helpful by itself. Because if I had a large distribution of outcomes, let's say there were 12 different things that I'm testing, and I'm trying to see if each one of them occurs, at a certain percentage. If this test is statistically significant, all it tells me is that at least one of my 12 outcomes didn't fit into the trend. And that doesn't exactly do a great job of telling you where your problem is. So it usually is step 1, I found out there's a problem, and then step 2, to isolate that problem. We're not going to be doing anything with the isolation of finding the problem, but in most situations, looking at the data, you should be able to take a very good educated guess as to where the issues are. Now we're still going to calculate our test statistic, which is chi-squared, and we're going to get our p-value, which on the calculator will just say p again. And we will finally do our interpretations. Now, before we get started with our example for this section, I just want to tell you guys that the calculator is going to ask us to not just put in the data, but it's also going to ask for the degrees of freedom. In a t-distribution, we didn't have to do the degrees of freedom because the calculator just took the sample size and subtracted 1. I honestly don't know why the calculator can't do a very similar thing here, but it can't. So, to put in the degrees of freedom, you have to figure out how many outcomes there are, and then you also need to subtract 1. So in this next example about M&Ms, you can see that we're going to look at a distribution of different colors in a bag of M&Ms. There are 6 different colors. That means when we go to input the data into our calculator, we were going to also have to put in that there are 5 degrees of freedom. Okay? So again, if you want to know why you subtract 1, the main reason is you can't do a distribution of size 1, which means if you tried to do a distribution of size 1, you'd have 0 degrees of freedom, and then whenever you would try to do the calculation by hand, you would end up getting an error. It's one of those things where they just want to make it very, very clear that you can't do size 1, because it just doesn't make any sense. All right? So here's what we're told about the M&Ms. Milk chocolate M&Ms are supposed to be 13% red, 14% yellow, 16% green, 20% orange, 13% brown, and 24% blue. They've taken a random sample of 200 peanut butter M&Ms and gotten the following distribution. Now, normally I'd have all this information plugged into the calculator ahead of time, but since this is the first time we're seeing it, I want to show you guys how I would go about doing it. So, the observed values, what they actually got, are the ones in the chart there. We're going to put those in first. So 25, 37, 45, 34, 19, 40. Let's start typing those in. So we go to our list, which remember is just stat, edit, to take ourselves into the lists. Now I might have to jump back and forth to double check these numbers. So we have 25, then a 37. Then we had a 45 and a 34. and finally a 19 and a 40. Now, some of you might be able to do the math in your head pretty quickly, and if that's the case, that's fine. So if you come back in the next column, we're going to do 13% of 200, 14% of 200, 16% of 200. Most of you probably know that whatever the percentage number is, you just double it, and that'll be the value. But let's say that it wasn't a nice sample, like it is now, of 200. What if it had been a sample size of like 583 or some arbitrary number like that? Most of you are not going to know that number off the top of your head. So here's a better way to do it overall for any sample size. So I'm going to plug in the percentages as decimals. So I got 13, 14, and 16, and these are going to go in list 2. So we got 0.13, 0.14, 0.16. The other percentages were 20, 13, and 24. So 0.2, 0.13, and 0.24. Now, once I've put in all those decimals, I'm going to go up to the top of the list and highlight L2, and now I'm going to tell the calculator to take 200, the sample size, times everything in L2. And what it's going to do is it's going to multiply all those decimals by 200, saving me a lot of work of going back and forth and multiplying. And again, if you wanted to do that ahead of time, you could, but I think that speeds up the process, especially when the sample size is something not nice like 200. Okay? So now I have what I saw happen in list 1, and I have what is supposed to happen if the M&Ms are perfect in list 2. So now I would ask myself, if I'm running this test, let's go through the whole process. Did they take a random sample of M&Ms? So if I look here, it says blah, blah, blah. A random sample of 200 peanut butter M&Ms yielded the distribution. Check, I got my random sample. Did everything fall into one category? We'll assume there's no multicolored M&Ms in the sample, so I think that's probably a pretty safe bet. Okay, if I go back and look, the expected values, those are the ones in list 2. Those are certainly all greater than 5, so I'm good there. And then finally, the last condition, if we come on back up here, is that did they give us a model? And of course, they did provide us with a model. We are comparing the peanut butter M&Ms to the milk chocolate M&Ms percentages. And so those percentages are a model. So random, check, model, check, expected values of at least 5, check, and for some reason my brain is escaping me on which one I just skipped over. Oh yeah, one category. And then, yeah, no multicolored M&Ms. So one category. All right. So now I can go ahead and state my null hypothesis. A lot of times you guys will email me about how you're supposed to do these, and I'm just telling you, these are kind of open-ended, but you just need something along the lines of this. I would say that my null hypothesis is the distribution for the colors of the peanut butter M&Ms is equal to the distribution of the colors of milk chocolate M&Ms. So I'm just saying that the distribution of colors should be the same for peanut butter M&Ms as it is for milk chocolate M&Ms. My alternative hypothesis is going to be that in at least one of the colors, and you want to make sure you say at least one, in at least one of the colors, the distribution of peanut butter M&Ms is different from the distribution of milk chocolate M&Ms. Okay? Yes, you're going to have to write out the words. They're going to have to be sentences. There's no quick symbols for any of this. All right? But we're ready now. We can go ahead. We can click on the button. We can type in stat. We can go over to tests. We can go way down towards the bottom to the goodness of fit test, which you will see on my calculator is option D. It's going to ask me, where did you plug in my observed values? And I put those in L1. The expected values I plugged into L2. And since there were 6 different colors, I'm putting in 5 degrees of freedom. And then I will come down here and I will calculate. So that test statistic probably not going to be all that meaningful to you, mainly because the test statistic fluctuates a lot based on the number of outcomes. So don't worry about that. What we do care about is the p-value. So we can see that this is going to be one of our wishy-washy p-values. 0.03 is greater than 1%, but it's less than 5 and 10%. So that means that this result, if I'm trying to be 90 or 95% confident, is statistically significant. I would reject the null hypothesis, and I have evidence to support that for peanut butter M&Ms, at least one of the colors is not in the same distribution as the milk chocolate M&Ms. But if I was going to try to be 99% confident, then the result would not be statistically significant. I would not reject the null hypothesis, and there would not be enough evidence to support that the distributions of the two different types of M&Ms were different. So that's how this works, guys. There's no big crazy difference. You're not going to come across some sort of question that's wildly different than this M&M question. You don't have to check any graphs to see if anything's a certain shape. You just plug in the numbers, you make sure they're large enough, you read the directions, you make sure the conditions are met, you plug them in, and you do your analysis. So I think for most of you, you'll find that this is a pretty darn manageable section. What I want you to do is a very small number of questions from the exercises. They start on page 688 of the text, and I only want you to do questions 1, 5, and 7. So E1, E5, and E7. So I will have the answers to those 3 questions in a separate video posted later in the week. Good luck to you guys, and I'll talk to you in the next video.